So the first thing we get into here in our new unit is section 1.8, which is actually review. You guys have seen all of these formulas before. In fact, half of them, if not more than half of them, you've seen in this class already before. Okay, so what are we talking about? We're talking about perimeter, circumference, and area of our four basic shapes. Okay, squares, rectangles, triangles, and circles. So starting out here with a square. Remember that perimeter is the distance around the outside of the object, the outside of the polygon. And so you can very easily just say that the perimeter is going to be your side lengths all added up. If you're writing down an equation, you can just say a plus b plus c plus d. Okay? But in a square, since all four sides are congruent, they're just going to simplify that to the perimeter is 4 times s, 4 times the side length. Okay? Make sense? All right, then area. A lot of you would look at a square and say, well, a square is like a rectangle. The area formula must be base times height. You've seen that before, right? And you can say base times height. And I'll give you full credit for writing down base times height for the area of a square. But a square, again, has 4 congruent sides. And so the base is s and the height is s. And so really the area formula is side squared, s times s. Okay? So there's our area and perimeter for a square. Any questions thus far? No. Moving on to the rectangle. For a rectangle now, again, we have our regular area formula for a rectangle, base times height. Okay. But perimeter, yes, you can still just say those 4 sides added up give you the perimeter. But in a rectangle, 2 of those sides, actually, I should say 2 sets of sides are going to be congruent. And so if we have B there, that means this one up top is also B. If we have H there, that means this one over here is also H. And so by finding perimeter, we could simplify that by saying our perimeter equals 2 times B plus 2 times H. Or if you want to get real fancy, you could factor out the 2 and say that it's 2 times base plus height. Okay? Either way, I don't care which way you work that. Okay, I tend to use 2 times b plus 2 times h. Okay, but that's how we find perimeter and area of a rectangle. Again, any questions? Again, none of this should be new to you. Let's go to triangles. Now, triangles, there is no guarantee, there's no guarantee that any of the sides are going to be congruent. Okay, and so for an equation to find the perimeter of a triangle is just a plus b plus c. We're just adding up those 3 sides. Okay? And then the area of a triangle, like we talked about briefly in the last unit, is 1/2 base times height. Now, where does that come from? Where does that come from? Well, that is from the fact that the area of a rectangle is base times height. Okay? And if I take a rectangle and I cut it with a diagonal, I essentially get 2 congruent triangles, right? And so if I want just the area of this one, I can then say that, well, that area must be half the area of the rectangle. So that's where 1/2 base times height comes from. Okay? Questions on the area formula for a triangle? Well, something else that has to be true. In fact, there's 3 things that have to be true. 3 things that I want you to write down. Item number 1 is that the base is always a side of the polygon. Okay? The base is always a side of the polygon. Next thing, the height is sometimes a side of the polygon. Be careful between those two. Base, always going to be a side of the polygon. The height is sometimes going to be the side of the polygon, not always. And the last thing I need you to remember here is that the base and height are always perpendicular. So the reason this is important, especially for triangles, is because if I have a right triangle, like we dealt with a little bit in the last unit, it's no big deal. I can just say, okay, this is my base, this is my height, and we're happy. Right? But what if I have a triangle that looks like this? And I'm not guaranteed that I have a right angle. Well, then I might say this is my base. Well, then this has to be my height. Height is always perpendicular to the base, 100% of the time. Okay, and so that's that case where in the first example there, the height is a side of my triangle, but in the second example, the height is not a side of my triangle. Okay, and sometimes you might have an obtuse triangle. And maybe they say that this part here is my base. Well, if that's the case, then to get the height, I have to actually extend out this side so that I can figure out where it's going to be perpendicular for my height. Because again, the height of an object is that vertical distance. If you're measuring yourself, you don't lean up against the wall like this and measure your height. You stand up straight and tall. And so it's that perpendicular distance from your feet to the top of your head. So same thing here. If I'm trying to push these triangles through a door, how tall does the door have to be? Well, it has to be that tall. My height. It has to be that tall. My height. Again, it has to be that tall. My height. To push these things through the door. Questions? Base and height can be in different spots for the same triangle. For example, it is possible, depending on what is given to us, for us to go ahead and use this side as the base. But if I do that, let me zoom in there a little bit. If I do that, then I have to make sure that I'm using this as my height. Okay, whatever side of your polygon you're using as your base, you have to make sure that you have a height that's appropriate for it. Remember, base and height have to be perpendicular. Questions? Nope. Okay. Then let's go ahead and try this example here. So botany club members are designing a rectangular garden for a courtyard in your school. They plan to place edging on the outside of the path. How much edging material do they need? Well, first and foremost, if you're uncertain what you're looking at here, this is the path. So if they're placing edging around the outside of the path, that means they're putting edging out here. So now, if we're calculating how much edging do we need, what measurement are we looking for? It's the perimeter. We're looking for the perimeter of this rectangle. Okay, so to do that, we have to know its base and height. So, look at the inside. Look at the actual garden. Do we know the base and height of the actual garden? Yeah, they tell us this is 16. Oops, helps if I have a pen going. This is 16. This is 22. Which one do you want to call your base? It doesn't matter, but yeah, okay, 16's on the bottom, so let's call it the base. Okay, so 16's our base. So if 16 is the base, what is the base of our edging? Bless you. There, take a look there. The path is 4 feet wide. And so if we're looking at the base of our garden, which is 16, but remember there's an extra 4 feet over here and an extra 4 feet over there. So it's 16 plus 8, which is 24 feet. All right, how about the height? The height, well again, this is 22, but we have an extra 4 feet up there and an extra 4 feet down there. So 22 plus 8, 30 feet is the height. And so we want to find the perimeter. And so again, remember how I'm grading stuff now. So if I'm finding perimeter of a rectangle, I've got to write down P equals 2B plus 2H. Because that right there is a point. I need to plug into that. P equals 2 times 24 plus 2 times 30. Because again, that is a point. Notice, don't do any calculations yet. All I do is plug in for the variables. Now I can start doing calculations so I can find out that my perimeter is 108. That right there is worth 2 points. But the problem is worth 5 points. The last thing I need to do is write down what kind of units I have going on. And in this case, it's feet. So just to recap, 1 point for the equation, 1 point for plugging in, 2 points for the correct answer, 1 point for the correct units. Total of 5 points. I'll give you guys a minute to work these two problems. You shouldn't need examples because this is what we were just tested on. Ready, set, go. Okay, let's work these out. Take a look at number 1, or part A, I should say. We're finding the circumference of this circle. Well, circumference equals pi dou. And so that means my circumference is going to equal pi times 15. Therefore, my circumference is 15 pi inches. But they wanted that rounded to the nearest tenth as well, so that means my circumference is approximately 47.1 inches. You needed to show all of that for full credit. Take a look at part B. Part B again. Circumference, crust equals pi dou. But be careful, the diameter is 8. They gave us the radius. And so our circumference is 8 pi centimeters. And make sure you give it rounded to the nearest tenth like they ask for. So 25.1 centimeters. We needed both answers for full credit. Question. If you had gone through and said circumference equals 2 pi r, just make sure you're plugging in the appropriate radius. Because again, the answer is still 8 pi. Yep. All right, so let's go to the back side of your notes. On the back side, we have a problem up here at the top. It says we want to make a rectangular banner. The banner is 2.5 feet wide and 5 feet high to the nearest square yard. How much material do you need? Well, first things first, I'm just going to draw a sketch of this. According to their description, this must be what we got going on. 5 feet high and 2.5 feet wide. Now I'm going to say 2.5. Is that okay? Yeah, 2.5 is still an exact answer, right? Because 0.5 is a terminating decimal. So it's still 2.5. I haven't rounded anything. I haven't changed anything other than put it in decimal form. Okay, now again, if I'm trying to find how much material I need here, what am I looking for? What measurement am I asking for? Area. Area. The amount of material I need here to make this banner. That's going to be area. It's not the distance around the object. It's how much material I actually need. So I got to find area of a rectangle. So the area of a rectangle is base times height. And so we're going to take 2.5 times 5. And so then our area is, well, plug that into a calculator. What do we get? 12.5 square feet. There's a problem with that answer. They asked for it to the nearest square yard. Okay. So if we want this in, yeah, but careful. The issue isn't the number. The issue is the unit. Okay. Square yard versus square feet. We can't do that. So we've got to take a little side conversation here. Let's talk about units of measure. So when we're doing area, we measure things in square units. It's square tiles, basically, right? How much can we cover that shape with? How many tiles can we cover that shape with? That's the whole idea. And so if I look at a square tile, my 1x1 square tile, and if I want this to be 1 yard and this to be 1 yard, then I am dealing with 1 square yard, that whole tile, right? Okay. Well, how many feet are in a yard? Something we should all know.
12.
There are 3 feet in 1 yard. There's 12 inches in 1 foot, but there are 3 feet in 1 yard. And so 1 yard is 3 feet. Again, 1 yard is 3 feet. And so I can take this 1 yard square and I can break it into 3 feet along that one side. And I'm just going to cut it across. Again, I can take this bottom 1 yard and break it into 3 feet going across the bottom. And I'm going to cut it across the whole shape. And so I might have 1 square yard, but how many square feet do I have? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you could say 3 by 3 is an area of 9, right? And so 1 square yard equals 9 square feet. That's how you're going to figure those things out. If they ask you for something in the nearest square inch, but they give you all your stuff in feet, you're going to have to figure out how many square feet is equal to the square inch, or vice versa, how many square inches are in 1 square feet. And you're going to need to be able to convert between those units. Now, some of you who are in physics right now or chemistry right now have done some unit analysis already, okay? If you have never done unit analysis, let me kind of give you the short and skinny of it. So we currently have 12.5 square feet, but I want square yards. So what I need to do is I'm going to go ahead and I'd like to call it a monorail or train tracks. And I just draw a big line. And what I have, I'm going to write right here. So I got 12.5 square feet. Extend that out, and I'm going to draw a line there. Okay? And I need to convert. Well, I want the square feet to go away. So I'm going to put square feet on the bottom. Square yards, which is what I'm converting to, on top. Well, I need an equivalent distance, or in this case, area. So 1 square yard, we just figured out, was the exact same thing as 9 square feet, right? And so now, this is no different than just multiplying 2 fractions. That's really all I'm doing here. And so square feet on top cancels with the square feet on the bottom, which leaves me with 12.5 over 9 square yards. So I know I need to divide 12.5 by 9, which tells me my area is approximately, I believe it's 1.38, right? Square yards. Now, I disagree with this question as far as why they would want that, because if I'm going to a store to make this banner, I do not want to buy 1 square yard of material to make this banner. I didn't buy enough. I would round it up to 1.5 square yards to make sure I have enough material. So let's be honest about what we're trying to find in a story problem. Okay? But that's how we convert that. That's called unit analysis. And that process can be done as many times as you need, meaning I might change something into, I don't know, let's say we have a light year. Okay, and I want to know how many miles per second that is. Okay, and I could go through and change this doing multiple conversions. Okay, doing multiple conversions, and each conversion I have, for instance, one of my conversions might be that there are, in 1 minute, I have 60 seconds. That might be one of my conversions. Okay, and I want to make sure that the minutes cancel from top and bottom, so on and so forth. And I can have as many of these fractions as I need, and I just multiply across the top, multiply across the bottom, reduce it, and that's how we get our answer. So take a look at the theorem here, or postulate, area addition postulate. Essentially says the area of a shape is going to be equal to that same shape cut into different pieces, the area of all the little pieces, as long as they don't overlap. So why is that important? Well, if I'm looking at this example, there's lots of different ways I could cut this up to help me out, but it's probably the easiest to simply say I'm going to cut it like this. Now I have 3 rectangles I could find the area of. Or I could cut it like that and cut it like this, because now I have 6 squares that I can find the area of. I know these are all 3 by 3 squares. And since this is 3 up here, that means this is 3 down there. This is all 3 by 3. Okay, because again, the whole side is supposed to be 9. 9 there, it's 9 down here, so 3 times 3 is 9. And so I know that I have 6 3 by 3 squares. And so if I want to find the area of this shape, I'm going to say I want 6 times the area of my square. Now I could use base times height, or if I wanted to, I could say s squared. That's fine. It's the same thing. So 6 times 3 times 3, well, 6 times 9 is what? 54. And this is square centimeters. Okay, so to find the area of an irregular shape, you want to basically cut it into shapes that you know how to find the area of, and then add them back together. Okay?